Hello and welcome to the MOOC on Applied Electromagnetics for Engineers. In this module, we will wrap up our discussion on transmission lines by discussing an important instrument that is used in many places in order to understand the faults, especially in the printed circuit boards, and in the older generation the problems in the transmission line cables, okay, long cables especially, or the instrument used in the power transmission to locate and isolate faults. This instrument is works very much like a radar by sending a known pulse or a known step voltage and extracting the voltage that comes back because of the discontinuities. We know that whenever there is a discontinuity, an incident voltage would be reflected from that point and then travels back towards the source or the generator. By monitoring this voltage which is coming back, you can then kind of locate where the load voltage is, and in fact you can also determine what kind of a discontinuity, whether it was an open circuit, a short circuit, inductive or a capacitive, when the reflected voltage comes back. And the instrument which does all this for you is called as a time domain reflectometer, and we will give you the basic principles of time domain reflectometer. Of course, the complete study of TDR is something that is beyond the scope of this subject. Now, as a warm up exercise to TDR, let us look at a few cases which I have drawn already here. So, I have a case A here where I consider a step voltage which is launched at t equal to 0 to the transmission line circuit, okay, of some length. We do not need to worry about what is the length of the transmission line here, but to know that the characteristic impedance of the transmission line is given by Z0, which is real, we will assume that, and the source is also having an impedance of Z0. So, in fact, we have to design an instrument such that the source impedance must be equal to the characteristic impedance. In fact, you can do that one, and when you do it, you have a pulse generator with an impedance of Z0 connecting to a transmission line of Z0. Let us say you now launch a step. As the step begins to propagate, it begins to propagate and arrives at the open circuit. What will happen to the because of the open circuit? There will be a reflected wave. What would be the shape of the reflected wave? The reflected wave would also have the same shape because gamma L will be equal to +1 here. So, the reflected wave will travel back. So, if you monitor the voltage at this point, which is at the input terminals of the transmission line, okay, and sketch what kind of a voltage you are going to observe, you will see that the voltage that you will see will be initially a launched voltage of some V0 by 2, assuming the step has an amplitude of V0. So, you see that the launch voltage step is V0 by 2 because it propagates there, and at time Td this voltage V0 by 2 will be further added because of the reflected voltage travelling back. So, you will see that at time t equal to Td the voltage will be 2, as jump of V0 by 2, therefore the total voltage here is V0, and of course this remains as it is because there are no further reflections, okay. Now let us look at the case where we have a short circuit. In the short circuit case, the initial voltage that would be reaching the step will be of V0 by 2, but because the short circuit has the reflection coefficient of -1, will invert the voltage signal and then send it back towards the source. So, if you now sketch what happens to the voltage at the generator or the input terminals of the transmission line, you see that initially you launch a voltage of V0 by 2 at time t equal to Td, or rather 2 Td, please make a correction in the earlier figure also. At time 2 Td, the voltage will actually jump down and become 0 thereafter. Now, if someone were to give you these two waveforms that we have sketched, you will be immediately knowing what kind of a discontinuity that existed, because here is a jump upwards of magnitude V0 by 2, therefore the total voltage that the generator sees will be equal to V0 after time 2 Td. Here the total voltage that the generator sees will be equal to 0 right after time 2 Td, therefore there is a voltage jump of V0 by 2, or rather minus V0 by 2. So, because in one case the voltage is jumping up and in the other case the voltage is jumping down completely, you can know very well that this is an open circuit case, this is a short circuit case, okay. Let us consider a couple of other circuits. Here we have the transmission line to be terminated with a load whose impedance happens to be equal to the characteristic impedance. And we know very well that if I start monitoring the voltage at the load side, I see there are no reflections. Why would I see no reflection? Because when the voltage here approaches, the step voltage of amplitude V0 by 2 approaches the load here, it will be completely absorbed. The reflection coefficient here is 0, therefore it would be completely absorbed. In other words, this is although the case of a infinitely long transmission line, right? So that the launch voltage would never come back. So this is the condition that you will have. Finally, if we go to the situation that is shown at this point, okay, so I have the characteristic impedance Z0 of the line, but I first terminate it with 2Z0, okay. If I terminate with 2Z0, I know that the reflection coefficient corresponding to that will be 2 minus 1 by 2 plus 1, which is equal to 1 by 3, but the reflection coefficient sign is positive, okay. So if you monitor the voltage up to 2 TD, you will have V0 by 2, and then you see a jump, and the magnitude of the jump will be V0 by 2 incident voltage amplitude times 1 by 3. Okay, so this is the jump that you are going to see. Again, by noting the difference between the case, say C here, this is the case B that we had considered, finally the case D that we have at this point. Okay, so this is the case C that we have. So you can clearly see that although there is a jump in case D, the jump is not of the magnitude V0 by 2. So therefore, this case D will be different from case A. In case A, the jump is actually completely V0 by 2, whereas in case D, the jump is there, but the amount is not V0 by 2, it is just slightly above. But if I know how much is the voltage jump, I can easily find out what is the value of the load that is connected, because I know what is the characteristic impedance, I know what is the amplitude of the voltage that we have sent in. So from these two values, knowing what is the jump in the voltage, I can find out what is the value of gamma L. Now if I consider the last case where we terminate the transmission line with Z0 by 2, what kind of a voltage do I get? I can find out what is gamma L corresponding to Z0 by 2 will be. So that would be half minus 1 by half plus 1. I am not really looking at the answer here, but to just understand that the reflection coefficient will be negative here, right. So the reflection coefficient will be negative here, and therefore instead of jumping up, you will actually see that there is a jump in the opposite direction. That is, you will actually see the voltage reducing at time 2 TD. Okay. So you see that if the voltage is jumping, you can immediately claim, which will be correct, that the load resistance that we have kept will be greater than Z0. If you see the voltage to be jumping down or going negative compared to V0 by 2, it is going in the other direction, then you will say that RL is less than Z0. So you can distinguish between two cases, RL greater than Z0, RL less than Z0. You can of course distinguish between the case of RL equal to Z0. For RL equal to Z0, there will not be any voltage change if you monitor the voltage at the input terminals. Okay, and by knowing the magnitude of the jump either in the positive direction up, that is above V0 by 2, or below V0 by 2, you can then estimate what would be the resistance of the load. Okay, so if I were to build an instrument that perhaps looks something like this, so I have a pulse generator. So this is the pulse generator that I have, and let's say there is a sync button for this, which will allow the pulse generator to synchronize with the oscilloscope. So please note that this oscilloscope must be a real-time oscilloscope. In commercial TDR, the oscilloscope and the pulse generator are built into the same kind of a system. Okay, from the sync you send out a trigger pulse. Okay, so this reaches the trigger input of the oscilloscope, so that will allow you to synchronize the two pulses. So when you are actually sending the pulse, so you need a t equal to 0 for your pulse generator, right. So that t equal to 0 condition is given by the syncing condition, or the sync to the trigger in. Then you actually have a pulse or a step generator. Okay, so you have a step or a pulse generator here. It could be both. So pulse TDRs also exist, step TDRs are also existing. What we do here is we divide this particular pulse which is having an amplitude, let's say V0 here, okay, so I consider an amplitude of the pulse to be V0. I consider, or rather I divide the power into two. So one, I connect this one to the device under test, and the other input I consider it to be the channel input of the oscilloscope. So this is the channel input for the display, okay. So this is the display to the channel that I have connected on the oscilloscope. So whatever device that I connect will be the device that I am testing. So when this step goes, the step will trigger the generator by the sync function. So whenever the step is generated, at this point the trigger pulse will send an input so that the oscilloscope is now triggered, and it will display the triggered step as such. And then when the step goes to the device under test, so there will be part of the step that would be already visible on the display, so it kind of just gives you a nice visual outlook, okay. However, any reflected voltage that comes back from the device under test that you have kept, it could be a transmission line, it could be a printed circuit board, it could be anything that you have connected whose faults you are trying to determine, that reflections because of the discontinuities would come back and would be further displayed, okay. So this is an example of what is called as a TDR scope, okay. So a TDR scope, by monitoring the voltage at the input terminals of the transmission line, allows us to say or find out the nature of the discontinuity and also the point at which you obtain discontinuity. Let us look at a few more examples. Let's say this time we start with a certain voltage that we measured on the TDR scope. So the output voltage of V0 by 2 is propagating at some time 2 TD, okay, as measured from the time axis that is present with the oscilloscope. We see that the voltage is of this nature. What can you conclude from this? You can see that initially the voltage must drop down. So initially there must be a element which acts like a short circuit, and eventually the element must act like an open circuit so that the complete voltage is reflected back. And an element which does so, initially acting as a short circuit and eventually acting like an open circuit, is a capacitor, right. A capacitor acts as a short circuit initially and then open circuits. Because of the short circuit, the voltage will completely go to 0 and then it will rise up to infinity. Assuming that this is the only discontinuity that I have, I can actually measure the charging time, okay. From there I can find out what is, from the value of tau, I can find out what is the load capacitor that I have used, okay. Suppose instead of receiving this type of a voltage, what I receive is a voltage that would look like this. So I have V0 by 2 and at some 2 TD, so I receive at some 2 TD, I receive a voltage that would go like this. So there is a jump of V0 by 2 and therefore the total voltage at 2 TD will be equal to V0. What kind of a load is this? This is a inductive load, okay. Now consider this case. Suppose I receive a voltage of this nature. Instead of going completely to 0, it just goes barely to 0 and then eventually starts to go and reaches V0. So initially you have V0 by 2. The jump here that you would see is not minus V0 by 2, it is only just a bit of a jump. So this voltage is not reaching 0. So all this voltage is remaining with us. So what kind of a discontinuity could this be? We know very well that the capacitor must act like a short circuit and hence will be pulling the voltage down, correct. But since the capacitor is not pulling the voltage completely down, there must be some resistive element, okay, which will be less than Z0. Otherwise this voltage would not have been less than like that. So there will be some resistance less than Z0 which is pulling the voltage down and then it is increasing to V0, okay. What I wanted to say is that initially you have a capacitance, okay, but the capacitance is not the alone discontinuity that you have. In series with the capacitance there must be an inductor so that a fraction of the voltage is actually developed, reflected back and then gets added to it. Eventually the capacitor will start to charge up to the full voltage and becoming a open circuit. So what you should have is not just a capacitor but also a load resistance RL, and the amount of jump that you would see would clearly be the voltage that the load RL will carry. So let us actually solve an equation for this. I will set up the equation and then I will give you the solution. You can verify this. So assume that we have a 2v plus L comma t, which is equal to v naught u of t minus Td as the pulse that would be appearing through the load or the characteristic impedance of a transmission line Z0 to this series combination of resistor RL and the capacitor CL. Okay. So if I call the voltage across this load as VL of t and the voltage across the capacitor itself as some VL prime of t. Okay, so I call this one as VL prime of t. Please remember, this part is the equivalent circuit, right? So this was the Thevenin equivalent circuit that we had, and then you have VL prime of t as just the voltage across CL, whereas the complete voltage across the discontinuity, which is RL in series with CL, is given by VL of t. What would be the nature of VL prime of t? We can see that if I kind of find out what is the characteristic, what is the charging time tau, I can see that the time constant tau must become RL plus Z0. How do I find the time constant? I make the source and short it to 0. So disconnect these terminals here in green and then find out the total resistance in the circuit. That would be RL plus Z0. So that is the equivalent R, and there will be a CL which corresponds to the total time constant of RL plus Z0 into CL. Therefore, the voltage across this load or across this capacitor VL prime of t initially will start at 0 because we had considered this to be equal to 0, and from there it will grow in the exponential manner to RL plus Z0 into CL. So I can write down VL prime of t as some V0, okay, u of t minus Td into 1 minus e power minus t minus Td divided by tau, where tau is RL plus Z0 into CL. Okay. What would be the current IL of t here? The current IL is given by CL dVL prime of t by dt. Please note that I have actually considered the voltage just across the capacitor, but if I calculate what is the current through this one, the same current will be in the entire loop here. So I can find out the current through the capacitor from that one, that would be the same current everywhere, and this is given by, if you evaluate and simplify the equation, you will see that this is given by V0 RL plus Z0 e to the power minus t minus Td by tau is the usual thing, and the voltages are starting after a time t equal to Td. You can now go back and calculate what is the full voltage VL of t, that is across RL and CL, and you will see that you will have two parts to this, V0 RL plus Z0, okay, which would be exponentially changing by tau, plus V0 1 minus e power minus t minus Td divided by tau. Okay. So this would be the total load voltage, of course this entire thing multiplied by t minus Td. What is interesting is the reflected voltage. You can go back and subtract the incident voltage from the previously calculated VL of t, and what you get from the reflected voltage is again two components. One component is V0 RL by RL plus Z0, okay, which would be decaying exponentially, right, with a time constant of the same value that we had considered, plus V0 half minus e power minus t minus Td, okay, this entire thing multiplied by u of t minus Td. So look at the nature of this reflected voltage. The nature of the reflected voltage is that at t equal to Td, the exponential term will be equal to 1 here, the exponential term here will be equal to 1. So half minus 1 will be minus half of V0, right. So it would be minus half of V0, which is the jump that you actually expect at time Td, for the reflected voltage, because there is a capacitor out there. But then this voltage would not be completely minus V0 by 2, but it will be added to this V0 RL divided by RL plus Z0. So the complete step of minus V0 by 2 would have been here, but then the actual voltage that you see is given by minus V0 by 2 plus V0 RL by RL plus Z0. So this V0 RL by RL plus Z0 is again very obvious. You started off with some V0 step voltage, okay, and then you had Z0, you had RL, the capacitor momentarily had become short circuited. So the voltage across this was 0, So the entire voltage VL of T was this fellow, which is simply from the voltage divider giving you V0 RL by RL plus Z0. Okay. Once you see a jump here, eventually the voltage starts to build up. So at T minus TD going off to infinity, this first term will go to 0, and in the second term here the exponential term will go to 0, and you reach some V0 by 2, asymptotically with a time constant of RL plus Z0 into C. And if you look at the source voltage now, so initially you are putting out a voltage of V0 by 2, and then there will be a jump here. The amount of jump that you are going to see down, which is not completely gone to 0, is clearly this one that is marked in the red circle. Okay. From here it will go on, eventually asymptotically reaching V0. Okay. So by looking at the magnitude of the jump, you will be able to find out what is the value of RL. On the other hand, if you obtained a voltage expression, that voltage waveform that looks like this on the TDR, which would not completely jump up but only jumps slightly up, okay, and then eventually go to 0, you know that this should have been the complete jump had only an inductor been present. However, because there is a gap now, right, this would more likely be inductor in series with a resistor. Okay, so there will be RL and some LL indicating a load, that is series combination of R and L. Okay, so this is how a TDR, by looking at the traces, will be able to identify what was the actual nature of discontinuity. Couple of points about TDR is that if you go back to the pulse generated at the TDR, this is the ideal pulse that one would like, so TR will be equal to 0. Okay. However, in practice the pulse that would be generated would more likely have a certain TR. Corresponding to this TR, there will be a certain bandwidth which is about 0.35 by TR, where about 99% of the power spectral density would have gone down. Okay, so this is about 99% in terms of the frequency, this is the power spectral density. So that bandwidth is about 0.35 by TR. If you are happy with 90% value, then you can even use a slightly non-conservative estimate of 0.24 by TR. Okay. Most importantly, if there is a fault, okay, so there is some discontinuity here on the transmission line, okay, and the discontinuity happens to be such that whose the location happens to be such that the time delay to reach the pulse, to reach here and then come back, would be less than this TR, then even as the pulse is changing slowly, right, this happens with a slow TR, the reflection would have come and then it would cause the total voltage to go something like this. I have not derived all this, but you can actually do that one by looking at the references which I would suggest during the course. So you would see that this amount of small distortions would not be visible properly and it can be completely masked. Okay, so if the rise time is slow, so a slow value of TR corresponds to a bandwidth in the range of say megahertz regime, will not be able to pick up faults or resolve faults. Why? Because when the voltage is changing from 0 to some value 1, let us say over a time TR, each point is traveling on the transmission line. So corresponding to a time change of TR, the corresponding length change on the transmission line here will be TR times U, where U is the velocity of the voltage wave here. So when the rise time TR is such that, or whatever the rise time that you have, any fault that would occur here, two faults let us say, will not be able to distinguish. So this is in fact the spatial resolution of a TDR type of an instrument, and it is the same as an optical TDR or as a simple radar. So whenever the rise time is slow, the corresponding length on the transmission line within which the discontinuities can be resolved, the spatial resolution will also be low. Modern TDRs can resolve or have a bandwidth of about 50 gigahertz or slightly greater than that, indicating TRs of about 7 picoseconds. Okay, so very short rise times, which means resolution, the spatial resolution is a few millimeters. This is impressive because any TDR that can resolve in a few millimeter where the faults are located is actually quite impressive. The reason being, you need to support a very high bandwidth. So the electronics that needs to support the very high bandwidths required by a TDR scope will also grow that much more expensive. Okay, so modern TDRs have TRs less than 10 picosecond and correspondingly large bandwidth and excellent spatial resolution. So which means any discontinuity which is just about a few millimeters will be able to be resolved. Okay, the corresponding capacitances and inductances that you can measure are very small. In fact, if you can measure capacitances of a few femtofarad, which is certainly not possible with a traditional LCR meters. Okay, traditional LCR meters cannot measure such very low capacitors, whereas a TDR can easily do that and in fact display nicely the corresponding graphs to you. Okay, so a catalog of TDR scopes are available in the internet. My suggestion is that look at the TDR scopes, okay, and then try to estimate from whatever the equations or from your knowledge of L, C and R, what should be the discontinuity so as to produce this type of a voltage. As an example, consider what happens if I have a series discontinuity of say R0, okay, on a transmission line. So this is all the transmission line having Z0 impedance, Z0 impedance. Okay, so if you are able to pin down what would be the TDR scope for this, then you would have understood not only how a TDR works but also understood how to calculate reflection. For your hint, you see that the impedance seen here is Z0, the impedance seen here is Z0, therefore the total impedance seen will be Z0 by 2 and that would appear along with R0. Okay, so you can see what would happen to the scope if you actually work out the equation, or you can see what happens to a series inductor with transmission line having Z0 here and having a Z0 over this side. So you can find out what would be the corresponding TDR scopes. So this brings us to the end of the first major subtopic that we have considered in the course. That major subtopic was transmission lines. We have understood transmission lines both from the steady state point of view as well as from the transient point of view. We will now begin to actually go to the second major topic, which is electromagnetics. Okay, so far we have avoided even bringing Maxwell into picture, but that was because we were able to get away with this analysis without using Maxwell's equations. All that was required was to extend the notion of voltages and the currents, and this extension is not trivial. It's not just simple that we have extended a voltage and a current. We have seen that on any piece of wire which will act like a transmission line, this voltage or a current will be in the form of a wave. Okay, so in the next modules we will actually begin by starting with a few mathematical preliminaries, then we will jump right into Maxwell's equations and then study the consequence of those Maxwell's equations. Thank you very much.